Okay, so by popular demand, since a number of people have asked about it, I'm going to talk about problem 2.15 in some greater detail. Now, um, let's go ahead and take a look at what it says over here. So problem 2.15 is a drug test problem. So what we have here is a drug test that when someone's a drug user, there's a 94% chance of successfully identifying them. And when someone's not a drug user, it gives a 9% chance that maybe that there's a false positive. And so a company drug tests its employees and it finds that 13% of them are positive for drug use. And so they want to know what percentage of the employees actually use drugs. And then, well, that's the first question here, and then some follow up information here or follow up questions. Now, the key thing to remember here is testing positive for drugs and actually using drugs are not the same thing, right? We see right away that just because you use drugs doesn't mean you will test positive. There's a 6% chance you won't. And if you don't use drugs, doesn't mean you won't test positive. There's a 9% chance you will. So there's error either way. So this 13% uh, of people who test positive, it's probably not 13% who actually use drugs. We actually have to do some work to figure out uh, what that is. And so before any of this can make any sense, and I recommend that you do this for every single one of these problems and not just this one, that whenever you're given some information here, right? Like it's 94%, a 9%, a 13%, that we turn that into useful information, right? We turn that into, we think of that in terms of the probability it represents. So this 94%, what is that? Well, it's a 94% chance of testing positive, right? But it's not for everyone testing positive. This 94% is just for people who use drugs who test positive, right? So that is the probability that you test positive given that you use drugs, right? And so that's this value here. All right. Now, the 9% then is also testing positive, but in this case, it's if you don't use drugs. So it's in the event drugs complement, right? It's at the complement of using drugs. It's testing positive, assuming you don't use drugs, right? And then finally, the last piece of information that we have, this 13%, it straight it straight up tells us that they test positive. So that's P of T. All right. So um, so this gives us three pieces of information, and we can now go ahead and try to make sense of all of this. So if I had my stylus, which I don't have it yet, I would probably uh, try to write this by hand, but I'm gonna go ahead and try this. So what we're given is P of, sorry, T given D is 0.92. And so when you're doing this on your own, or 0.94, I would recommend uh, taking notes about these problems while you work them out. Probability of testing positive given that you don't use drugs is 0.09. Uh, testing of testing positive given you don't use drugs is 0.09. And then let's go ahead and overwrite this with just probability of testing positive in general is 0.13. All right. And so at this point, we have a number of probability rules under our belt. We should know, let me scroll up here. These are all in in the textbook scattered about, but here I've consolidated a bunch of them in this handout. We know the rules for complement events. We know the union rule, and I discussed this in the introduction to probability video. And we know how to compute the conditional probability, and we also discussed that in this video. And then we have a bunch of rules about independent events which don't really apply here because hopefully uh, taking drugs and testing positive for drugs should not be independent events, right? You should have a better chance of testing positive if you use drugs. Otherwise, it's a pretty useless test. So this doesn't really apply to us. And in the Bayes theorem video, I also introduced this fact that the probability of some event is the probability of that event given some other event times the probability of that other event plus the probability of the first event given the second event doesn't happen times the probability that the second event doesn't happen. And the essential idea behind this is, all right, let's say if you use drugs, there's a 94% chance you test positive. If you don't use drugs, there's a 9% chance you test positive. So how many people actually test positive is going to depend on how many people use drugs, right? And so if everyone uses drugs, that's 94%. If no one uses drugs, that's 9%. And we're looking at something in between, right? And it should be pretty small considering that it's pretty close to the 9%, right? So, 4% of people use drugs, then we get 12.4% testing positive. So that's pretty close. But we want to solve this exactly. Then what we want to do is solve this linear equation here. Now, the reason we know to use Bayes' theorem as opposed to anything else is, well, if we look at the other formulas that we have on hand, they don't really match up with anything that we have going on right now, right? We have stuff about unions and intersections, and we don't have information like that. And what we have instead is two conditional probabilities, right? And so there's two ways we could try to apply Bayes' theorem. We could say that P of t is equal to P of t given d, P of d plus P of t given d complement 1 minus P of d. All right, that's form number one. And the second form of Bayes' theorem is we just replace the rules of P and D. P of D is equal to P of D given T, P of T plus P of D given T complement 1 minus P of T. Oops, I'm missing a parenthesis there. All right. And so we can look at these two, show this one over here, these two formulations, and these are both true statements, right? And we can ask, all right, which one's useful? Like, which one is, they're both true, but which one's actually useful to us in this scenario? Like, well, I know T given D, I don't know T given D complement, those are these values here, right? I don't know P of D given T, and I don't know P of D given T complement. I do know P of T. So in this first equation, there's 4 unknowns, but I can identify 3 of them. In the second equation, there's 4 unknowns, but I can only identify one of them, really. I can just identify P of T. And so you want to be in the scenario where you know more. That's like just the better place to be. So let's go ahead and get our pencil here, and let's scratch that out. That's not useful to us. So let's go with this first thing here. So if that's what we're working with, then okay, what does that look like? That looks like, well, P of t, do I know what that is? Sure, it's 0.13, right? Is equal to P of t given d, 0.94 times, well, I don't know what P of d is, right? Plus, and then P of t given d complement, we know that is 0.09 times 1 minus P of d, and again, I still don't know what P of d is, right? But, hey, this isn't looking so bad, because once I have this, so look, okay, this is a linear equation with one unknown, right? I have uh, P of d's, a bunch of numbers, multiplied and added to it or subtracted, and the only thing to do now is I'm going to shift over here for the space. The only thing left to do is to, I'm going to need a way bigger one. The only thing to do is just to solve this, just like you would any other linear equation, right? P of d is essentially x in this case, and we want to solve for that. So 0.94 P of d plus, we distribute this 0.09, 0.09 minus 0.09 P of d. Now, let's go up here, a little bit more space here. The first thing I want to note is I have a 0.94 P of d, and I'm subtracting from that 0.09 P of d. So that all simplifies to 0.85 P of d, right? Plus 0.09. So that's just some algebra here combining the like terms. And the second thing I can do is subtract 0.09 for both sides. So what I have is 0.04 is equal to 0.85 P of d, right? And so then finally what we get is that P of d is 0.04 divided by 0.85, right? And this if you wanted a more precise formulation of that, is this expanded term right here. So I could just take that, go over here, pop it in there, and hey, I think this would be a good time to go ahead and try to submit an answer. And, you know, shockingly enough, it marks these two as wrong, but yeah, my probability of using drugs here is correct. And of course, we correctly identify what each of the probabilities mean. All right, so hopefully that's helpful to us. I'm going to not do all the details about the rest of this. I'll just say, generally speaking, oh, that looks terrible, but all right, we'll live. This is maybe the worst Venn diagram of my life. I want to get a stylus, this will be much better. So let's say, oh, wow, okay. So once you are in a situation like this, right, where you know P of D, we know P of T, you want to try to fill out a Venn diagram with all of the probabilities. So it's going to look something like that. And what you want to first start by finding out is what's in both D and T. It's like, well, what's in both D and T, we recall briefly, right? that P of A and B is P of A given B times P of B, right? That's multiplying both sides here by P of B. So I would go over here, I can say, well, let's go back to my text box. P of T and D is equal to P of T given D times P of D. And the reason this is significant is I now know what P of D is, right? And I know what P of T is, or P of T given D is. So all of this is equal to 0.94 times, well, what we have here, 0.04706, let's say. Let's do 4706. And we want to know what that is. That's about 0.044235. What does it say? 0.044235. Yep. Okay. So I can go to my Venn diagram here. I can go in the middle here. I'm typing 0.044235. All right. Now, I still need to fill in something here. I still need to fill in something here. And I still need to fill in something here. Right? But I'm not going to go into all of these details at this point. I'll let you guys work some of this out yourselves. But what we know is that in the drug circle, 0.044235 plus x is 0.4706, right? So there's a linear equation right here that'll tell you what x is. The sum of everything in the circle has to be P of D, which is 0.47. Oh, I see. I wrote this over something. Yeah. Oh, this 0.04 over 0.85, but it's closer to 0.4706. Right. This and the y together have to form the entire t circle, which is 0.13, right? So when I put this and the y together, that's 0.13, so there's a linear equation that tells you what t is. Once I know what x and y are, everything inside the box has to add up to 1, right? Because that's all of our possibilities. You're either this area here is used drugs and tested positive, used drugs and didn't test positive, tested positive and didn't use drugs, and then neither tested positive nor used drugs on the outside, right? So once, those are the only 4 things that can happen. So once I put this information here, I can find x, I can find y, and with x and y, I can find z, so the whole thing sums up to 1. And then any of these questions is just a matter of figuring out, okay, which regions of my Venn diagram satisfy these descriptions. And once you have those, then you just count up the values of those regions, and you got those probabilities. All right. And it's also worth noting that at the end of this handout, there's a example problem that works through a lot of it's a problem with a very similar setup, and it works through quite a few versions of questions that could be asked. So you might find it helpful to go through that and see what's there. All right. Well, hopefully that was helpful. Oh, one last thing. One other thing that's worth noting. So here in our visualizer, we have 94%. right? Chance of testing positive if you use drugs, 9% chance if you don't. If I just want the x value, the probability of x to be 0.13, then what y has to be is 0.47058824, which is what we said it was going to be, right? So 0.47055824. All right, let's zoom in a little bit. Ooh. It's a little hard to read at this point. Let me pull this to the side. And then what we have here are 4 regions, right? Which correspond to the 4 regions of the Venn diagram here. You can fill in all those values, and then once you have all the Venn diagram regions, it's just a matter of reading the remaining problems carefully and figuring out where those things should go. All right, great. If you have other questions, please let me know.